I should go first of all.
Oh, yeah.
No, first thing to report.
Perfect. Thank you. Sure.
Haven't looked at it for
All right, well, hello and welcome to the Simons Institute. My name is Peter Bartlett. I'm the Associate Director here. We run these collaborative programs every semester, and welcome to the first workshop for the program on the computational complexity of statistical inference. We've got we need to say thank you to the NSF for its support of this program through the Foundations of Data Science Institute. And this first workshop is called Rigorous Evidence for Information Computation Trade-offs. A big thank you to the organizers, to Sam Hopkins, Lenka Zdebarova, and Afonso Bandera. Let's thank them. It's an exciting program. I'll hand over to Sam in a moment to introduce the workshop. I want to say a few words about logistics. You should have discovered the food and drinks outside. There for the breaks, for lunch, you're on your own. There are lockers across the way on the far side of the building on this level if you need to leave some things here. We have everything going in a hybrid format this morning. So, you know, there are Zoom speakers and audience on Zoom, as well as the usual video on YouTube and the website. So everything's being archived. Our videographer in the booth here is Omid Farr. We'll be helping out with hooking up computers and so on. Also, just to introduce Kailani Penland in the back. So she's the one that's done, she and Ashley Hassan have done all the local arrangements for the workshop this week. So a big thank you to Kailani and Ashley also. And if you have logistical questions, Kailani's the one to ask throughout the week. Okay, Sam.
Thanks, Peter. So it's amazing to see all of you here for this kind of amazing reunion. We realize the world is still a tumultuous place and some of you are on Zoom, so welcome to our Zoom audience. Hello, I think that's the camera. We're doing something a bit new. We have a mirror workshop going on this week at EPFL on Tuesday, Wednesday, and Thursday. So a bunch of our European participants are converging there. They will have their own talks in European morning. And then Tuesday, Wednesday, and Thursday, we will have some joint sessions that I hope you'll join us for, with talks and questions from both audiences. So we've opted for a pretty broad interpretation of the subject matter. So you'll see that we're going to deepen our investigation of some themes which came up already in the boot camp: statistical query algorithms, low degree algorithms, sum of squares algorithms, approximate message passing, overlap gap property, things like this. But we also have a bunch of talks from kind of adjacent areas, and we're hoping that we can take this opportunity to build new connections. So we have talks about landscape of high dimensional optimization, proof complexity, worst case to average case reductions, average case to average case reductions, time space trade-offs. We even have some talks about quantum computing and quantum information, and on differential privacy. So we're hopeful that we've brought together sort of a crowd with enough overlapping interests to make some progress, but a disparate enough set of expertise that we can build new connections. We hope that you will take this opportunity of being here in person to actually have some of those conversations. Logistically, to the folks on Zoom, to lower the burden on the session chairs, we're probably not monitoring the chat super carefully. So please unmute yourself and ask questions. Feel free. If you are a Zoom panelist and you can see questions from Zoom participants who can't unmute themselves, if you could just raise those questions for us, that'd be great. You'll notice because of the overlapping session with EPFL, we do have a slightly different schedule Tuesday, Wednesday, and Thursday as compared to today and Friday. In particular, we have a pretty early start. I'm hopeful to see some of you here for talks that overlap with EPFL at the next few days. And as a reward, we get out early on Tuesday, Wednesday, and Thursday. I think talks are over at 2:15 or something, and there's plenty of time to talk. And on Friday afternoon, Michael Celentano has been voluntold to lead a hike in the Berkeley Hills for all of us. So thank you, Michael. You can meet him outside the building at 2 on Friday. We'll remind you of that a couple times. Finally, thank you to Afonso and Lenka, my co-organizers. You were awesome. Thank you to Guy and Sleel, who gave us the opportunity to organize this. Thanks to the Simon staff. You are all awesome. This couldn't happen without you. So let's move on to the first session. It's my pleasure to introduce Pravesh Kothari, and after him, Aaron Petechin. Due to some organizer cronyism, the workshop is kicking off with two of my oldest collaborators talking about a subject near and dear to my heart. Pravesh and Aaron have been at the center of developments on sum of squares algorithms and lower bounds for the last 5 or more years. Take it over, Pravesh.
All right, can you hear me? Thanks for the fantastic introduction, Sam. Thanks also for organizing this workshop to Sam, Lenka, and Afonso, giving me the chance to talk in person after like more than a year, and all of us hanging out in Berkeley. That's super great. So I want to tell you about a very recent work on refuting constraint satisfaction problems, jointly with an amazing graduate student at CMU, Peter Manohar, and my colleague, Venkat Guruswamy. So let me start by telling you the central object of interest in this talk, which is this algorithm called a refutation algorithm. Okay, so a refutation algorithm gets as input an instance phi of a constraint satisfaction problem. And for the duration of the talk, my running example of a CSP would be the k-sat problem. So this is simply the CSP where you have sat clauses, each of width k. Okay. So given such an instance phi of k-sat with m clauses and n variables, the goal of a refutation algorithm is to output a value v in 0, 1, such that v is an upper bound on value of phi. By value of phi, I simply mean the maximum fraction of constraints that the best possible truth assignment to the variables can satisfy. Okay. Now we say that the algorithm succeeds in weakly refuting the instance phi if it outputs a value which is strictly less than 1. And the way you should think about it is that in this case, the algorithm is giving you a convincing certificate that the input instance is unsatisfiable. You can, be more demanding and ask for a strong refutation, in which case the value should be less than 1 minus delta for some absolute constant delta bigger than 0. And in this case, the algorithm is convincing you with a certificate that no more than 1 minus delta fraction of the constraints can be satisfied by any assignment. Okay. Now, this is the natural co-NP analog of the problem of solving max k constraint satisfaction problem that you might be more familiar with. And in the worst case, these problems are actually equally hard. So our goal would be to find the largest possible family of instances phi. They have got to be unsatisfiable if I've got to refute them, for which I can get non-trivially efficient algorithms. Okay, so that's my goal. A lot is known for this problem, and I'm going to summarize our state of knowledge in 2 slides. Okay, I'm going to start with first the worst case story here. Okay, so here's what we know for worst case k-sat instances. The problem, so this curve, by the way, has the number of constraints drawn in log scale on the x-axis, and the best running time we know for refuting worst case instances with a given number of constraints on the y-axis. Okay, so in general, you should expect that CSPs should get easier, or refuting CSP should get easier if you have more constraints. Intuitively is because, if you have more constraints, you can hope for like some local violations to arise, and you could, use those local violations to conclude that no assignment can satisfy all constraints. Okay. Regardless of this intuition, it turns out that in the worst case, algorithms, notice like, there's a non-trivially sub-exponential time algorithm, meaning better than like, let's say brute force 2 to the omega n time algorithms, only when m exceeds n to the k minus 1. Okay, so that's the first inflection point. Then there's a sub-exponential time algorithm, which becomes a polynomial time if you have omega n to the k constraints. So what I want you to remember from this is the 2 relevant points where the curve changed. At n to the k minus 1 and above, there is a sub-exponential time algorithm. And at n to the k and above, there is a polynomial time algorithm. Okay. Let me draw the same picture for random instances of k-sat now. Okay. By random instance, I mean that variables in each clause are chosen uniformly, randomly, and independently. And then the literal patterns on the variables are again chosen uniformly, randomly, and independently. Okay, so both the so-called clause structure or instance hypergraph is random, and the literal patterns are random. This is natural to study if you are like, depressed by the grim picture in the previous slide. And indeed, you get significant gains in the sense that the picture looks significantly different from the one we just drew for worst case k-sat problem. Okay, so what do we know about this? Well, it turns out that there is a special number, n to the k over 2, that is often called the spectral threshold, beyond which there are polynomial time algorithms for refuting k-sat instances. Okay, it's called the spectral threshold because, as I'll soon show you, the algorithm that does this is a certain spectral algorithm. Okay, but actually, even below n to the k over 2, you can get a non-trivial improvement over brute force search. There is like a non-trivial structure in the problem even below this density. In particular, you know that for any integer parameter L, there is an n to the O of L time algorithm that succeeds in refuting so long as you have this weird many constraints. Okay, and actually it's not so weird, and the way I like to read this trade-off is really in the way it's written here. So here is a way to understand it. Let's see if I remember how to use a clicker. Oh, hey. All right, so this term stays the same. And when L grows from 1 through n, the second term goes from n to the k over 2 minus 1 to basically order 1. So what's happening is, as L increases, the lower bound on m required goes from n to the k over 2 to n. So in some sense, the parameter L gives you a way to interpolate linearly in the exponent of n the number of constraints. And so what's happening is that, there is a linear relationship between the exponent of n in m and the running time we know for refuting instances with that many constraints. Okay, and as just an example, if you were to specialize it in the case of 3-sat, then it turns out that there's a 2 to the n to the delta time algorithm for any tiny delta that succeeds whenever you have n to the 1.5 minus delta over 2 constraints. Okay, good. So that's not all. There is an even more interesting behavior that seems to happen in the case of random k-sat instances. There's a third interesting point in the curve discovered in this work of Feige, Kim, and Opek, a really fascinating work, and some extensions proved in David Whitmer's CMU thesis. Basically, these results show that there are polynomial time verifiable refutations, meaning polynomial time verifiable certificates that can convince you of unsatisfiability of random instances with number of constraints which is polynomially below the spectral threshold. Okay, so there's some constant delta k such that if you have only n to the k over 2 minus delta k constraints, for that many constraint instance, you still have with high probability a certificate that will convince you of unsatisfiability. The key difference, of course, is that we don't know any polynomial time algorithm to find such certificates. In fact, the best algorithm we know runs in some fixed sub-exponential time. Regardless, they exist. Okay, and we don't know of an analog of this phenomenon in the worst case. So this is like some truly new phenomenon that we are seeing in the random case. Okay, good. So we saw two pictures. That's a summary of the knowledge of solving k-sat or refuting k-sat. And if you're a complexity theorist, at this point, you might be wondering, well, how does the complexity of k-sat interpolate between these two extreme worlds, right? One might get the sense that random k-sat is perhaps too idealistic. It's a specific natural distribution. After all, maybe like my instances are not going to look as random k-sat instances do. Or you might think that the worst case picture is too pessimistic. There are non-trivial algorithmic techniques that people invented for solving the random instances. You might think, well, do they apply to more general random instances or not? And in general, you might be wondering, how much randomness is needed for these techniques to actually work, for our refutation algorithm to succeed, right? Does clause structure need to be random? Does literal patterns, do they need to be random? And so on, okay? So what I want to tell you today, the main punchline of this talk, is that modulo whether you buy the next model makes sense or not, there is a satisfactory resolution to all these questions, okay? So let me tell you this model, and let me tell you the main results. The model is the smoothed CSP model introduced by Feige in 2007. And here is what it does. It starts from a worst case instance, so like absolutely arbitrary instance, And then you just perturb the literal patterns independently with some small constant probability. Let's say 0.01. Okay. So the thing to notice is that the clause structure, or the so-called instance hypergraph, is completely arbitrary. Only the literal patterns have this, small amount of randomness introduced by the random perturbation. Now, it's very easy to prove that with high probability over the choice of the smoothenings, the true value of the resulting smoother instance drops, in fact, is bounded away from 1 with high probability. Okay. And so it's legit to ask the question of refuting such instances. And that's exactly what Feige did. And the main result of this talk, the algorithmic result of this talk, is actually this picture. Now, this picture might look exactly the same as the one we drew for random. And that's by design, because that's exactly the result, that we can draw the exact same curve for refuting random, exact same curve for refuting smoother instances, strongly refuting smoother instances, as we could for random instances. Okay. So that's the main algorithmic result. Let me just quickly tell you about the context of this result, what we knew earlier. So I already told you what we knew for random. For more general instances, much less is known. So, this work of Feige gave a weak refutation algorithm instead of a strong one that we are getting now. For the case of smoothed 3-sat instances with n to the 1.5 clauses. Okay, so this algorithm was a polynomial time algorithm that worked for that many constraints. Now, to actually get this algorithm, Feige invented a combinatorial notion of refutation certificates. That's what he used to get this. And as a result, they generalized to 3 CSPs, other 3 CSPs, but not to, arity 4 CSPs, or not to strong refutation. Okay. And finally, there is this recent work, in fact, the direct inspiration and precursor to this work, which, occurred in a joint work with Venkat and my student Jackson Abascal last year, where we gave a strong refutation algorithm for a slightly weaker model than smoothed. It's called the semi-random model. Briefly speaking, it just means that, instead of perturbing the literals, you are completely going to set them to random values. Okay, that's what semi-random means. So for semi-random k-sat instances, we gave a polynomial time algorithm with n to the k over 2 constraints. So you can think of this as getting, one end of the curve. So let me summarize the knowledge to you so that you don't bother by the bounds. Yes.
Some question about this smooth k-sat model. So
yes,
if you're perturbing every literal with probability 0.01, then there's still, for every clause, there's a constant probability that every literal in it got randomized.
Yes.
And so don't you just have a semi-random instance hiding in your smooth instance?
Yes, absolutely.
Okay, so should I really think of semi-random as a weaker model?
Yeah. I mean,
a loss of a 2 to the k or something.
So here's the cool thing, right? For the purpose of strong refutation, the two models are exactly the same.
Yeah.
By exactly the argument you just said. But for weak refutation, you have to worry about these things. Because for weak refutation, you are proving really a less than 1 bound, and that can actually okay, in some sense, the techniques we have for weak refutation don't really go between smoothed and semi-random case easily. But for strong, in fact, that's exactly going to be the case. In fact, most of the talk, the technical part of it, I'm only going to focus on semi-random, which you anticipated. Perfect. So to summarize our status of knowledge, for random, we knew this trade-off. For semi-random, we knew one end of the trade-off, meaning L equals O of 1 case. And for smoothed, we knew of no strong refutation algorithm, even for 3-sat. Good. So that's the algorithmic result. What about this FKO style certificates? So again, exactly the same curve now we can draw, even for smoothed k-sat instances. Okay. In other words, we're gonna be able to prove that there is some density n to the k over 2 minus delta k for some fixed constant delta k, at which polynomial size certificates of unsatisfiability exist for all smoothed k-sat instances. Yes.
Specific to SAT or for other CSPs too?
Yeah, excellent question. So k-sat is my running example, but there is a right generalization of all the results, both algorithms and certificates, to all CSPs. Okay. And so yeah, you can ask me offline about them, but I want to focus on k-sat just for the sake of whatever, numbers being easy and exposition being somewhat simple. Good. So that's the result. So you can think of this as a generalization of, in fact, I would argue even a simplification of the FKO result to arbitrary clause structures, like no randomness. And the key ingredient, which I want to spend a few minutes on, is a resolution of a conjecture that Feige made in 2008. Okay. Now, if you were, bothered by all these curves and bounds, etc., I asked that, you can come back up, because I'm going to tell you a completely plain, pure combinatorial fact, which has ostensibly nothing to do with CSP refutation, which makes sense without any CSPs. And so you can enjoy it without even following whatever I said so far. Okay. So Feige's conjecture is a certain extremal conjecture about girth of hypergraphs. Okay. In order to understand it, let's try to ask it for graphs. What's the Feige's conjecture if it were to be made for just plain simple graphs that we are fond of. Okay. So here's the question. Suppose we have a graph on n vertices and n times d over 2 edges for some parameter d. Okay. The reason I'm writing it in some awkward way like this is because I want to think of d as the average degree of the graph. Okay. So my question is, what is the maximum possible girth of such a graph? As in, what is the maximum possible length of the smallest cycle that can happen in such a graph? Okay. If d is 2, then the number of edges in the graph is exactly n. There's got to be one cycle. And you can really take the graph which has, is a single n cycle. So clearly, in this case, you can make a graph with that many edges and a cycle of length n and no smaller, which means that in this case, the girth can be as large as n. It turns out that if d is even tiny bit bigger than 2, then the girth drops to logarithmic factors in n. So in particular, Alone, Huri, and Lineal prove that the maximum girth of such a graph is up to a factor 2, simply log to the base d minus 1 of n. Okay, and it turns out that up to this factor 2, this bound is in fact even sharp, via some explicit Ramanujan families. So that's the question for graphs, and we want to ask the same question for 3 and more generally k uniform graphs, k uniform hypergraphs. Okay. But before that, I have to tell you, what does it mean to be a cycle in a hypergraph? So we're going to identify some property of a cycle in a graph and then use it to generalize. A cycle you can think of in a graph as a subgraph, meaning a collection of edges that touches every vertex an even number of times. Right? In fact, if you were to define a cycle in a graph exactly in this way, you would come up with the same girth path. So that's what we're going to use to extend to hypergraphs. Okay. So some people call them even covers, as you'll see very soon why. Because a hypergraph cycle, generalizing this definition, is simply a collection of hyperedges that touch each vertex of the hypergraph an even number of times. Okay. So, if there are some people who enjoy coding theory in the audience, or maybe feel better about coding theoretic interpretations, then one reason people in coding theory care about hypergraph cycles and Feige's conjecture is because it actually relates to rate distance trade-offs for linear codes of certain kinds. Okay, so so how does this connection come about? So you can think of a k uniform hypergraph as describing a set of coefficients to linear equations modulo 2. Simply think of each hyperedge as telling you which coefficients are set to 1 in the corresponding equation. If you do that, then a cycle is simply a subset of equations which are linearly dependent, in the binary field in F2. And so a hypergraph cycle is simply the length of the smallest linear dependency in a set of k-sparse linear equations modulo 2. Okay, good. So now I can tell you what Feige conjectured. So he conjectured that if you have a k uniform hypergraph with n times n over L to the k over 2 minus 1 hyperedges, if this reminds you of the trade-off we wrote earlier for random k-sat, etc., well, it's not an accident, they are very related, as a cycle of length about L log n. Okay, just to make sense of it, if you try to specialize it to k equals 3, then this is saying that if you have n to the 1.5 over square root of L hyperedges in a 3 uniform hypergraph, then it must have a cycle of length L log n. Now, before even going further, notice that this is significantly different, or perhaps a little bit different at least, from the case of graphs. In the case of graphs, once you have more than n edges, it seems like it has a log length cycle. In this case, however, for you to see a log n length cycle, you need to have n to the 1.5 hyperedges. And then there is this trade-off between the length of the cycle as the number of hyperedges drop from n to the 1.5 to n. Okay. All right. Now, because this is a weird trade-off, you might think, well, is this the best possible thing one could conjecture? It turns out it is. because you can construct simply random hypergraphs with slightly smaller than this number of edges and prove that there is no cycle of this length. So, if you want a cycle of this length, then even random hypergraphs tell you that you're going to need at least that many edges. Okay. Yes.
So is this easy to see for regular or like for the simple graph case, if it's regular, it's quite easy to see?
Yes. I actually don't know of a simpler proof for regular case either. It's a good question.
So okay, just maybe I'm getting ahead of this, but this number is the same as the
Yes.
reputation thing.
Absolutely the same.
So can you view, like in the reputation, the spectral reputation algorithm for the random case, you do this like trace moment calculation if you want to bounce some spectrum.
Yeah.
And can you reinterpret that calculation as like the expected number of these?
Exactly what the proof is going to be.
Proving an average case version, like the random
Yeah.
version of this theorem. Okay.
Absolutely. In fact, yeah, this is the only part that I'll actually do in the talk. So yeah, Sam, you're anticipating perhaps my slide number n-1. Yeah, absolutely. Good. So yeah, that's the conjecture. So let me tell you a little bit about what we know about this conjecture. Okay. So first thing I want to tell you is that even though this conjecture ostensibly is only about a single L log n cycle, you can very easily derive from it that there are not just one cycle of that length, but in fact you can have edge disjoint cycles about m over L many of the same length. And the proof is very simple. You take a cycle and just like peel off all the hyper edges and repeat on the residual hypergraph. Okay. So that's great because this is the connection that matters when you're applying it to CSP refutation. So, what we know about this conjecture is for the random K uniform hypergraphs, this work of Feige, Kim, and Ofek, this was their key result. This was their like main combinatorial construction. They proved that for random K uniform hypergraphs, the conjecture is true. Okay, and because the graphs are random, they proved it, the way we actually prove such theorems in general. They use the second moment method, and like you're trying to understand the probability that a certain structure exists in a certain random hypergraph. So you're going to use second moment method and argue that it exists. Okay. For worst case hypergraphs, actually let me skip this connection right now. For worst case hypergraphs, the story so far is that we know how to prove this conjecture for L equals O of 1. It was actually done in this paper of Asaf Naor and Verstraete, and then improved parameters a little bit by Feige. The upshot of all these works is that for L equals O of 1, we know that the conjecture is true up to a factor of log n. The best bound for like larger L, however, is due to Alone and Feige, who proved that for 3 uniform hypergraphs, if you have n square over L many hyperedges, then in fact there is a L log n length cycle. So this is off by the true trade-off by a square root of n over L factor. Okay. So long story short, the summary of previous works is that we kind of know the conjecture for L equals O of 1, and there were several combinatorial approaches to attack this conjecture, but basically, effectively speaking, we do not know what happens when L is larger than 1. Okay. So now I can tell you what we prove. We basically settle the conjecture. We prove that for every K and L, Feige's conjecture is true up to a polylog n factor. Yes.
You said it's slack of log n, but the alone Feige bound has an n square versus n to the 1.5.
So this result is a Naur, Verstraete, and Feige result. It proves the conjecture for L equals O of 1. For this case, we know the conjecture is true up to like an additional factor of log n in the density m required. So in other words, we know that if you have n to the k over 2 times log n many hyperedges in a K uniform hypergraph, then there is a cycle of length order log n. But we don't know this conjecture for L bigger than 1, or we didn't know it for that case. The alone Feige bound actually holds for all L, but it's a weaker bound and it holds only for 3 uniform hypergraphs. It the slack is root n over L here. Good. Perfect. So yeah, so that's the key result that actually goes into proving this existence of certificates that I was talking about earlier, the proof of Feige's conjecture. And as Sam kind of anticipated, the argument is going to be a spectral algorithm, a spectral argument instead of like a combinatorial one. And I had to give it a name, so I chose to give it spectral double counting, and I'll try to justify it to you when I actually show what this argument is. But basically, it's a connection between existence of hypergraph cycles and sub-exponential size refutations of the kind that we were looking for, in our algorithm design question. Okay, so we're going to like settle this purely combinatorial looking conjecture by looking at our refutation algorithms later on. That's it. Yes.
So
For your actual result for like smooth CSPs, do you actually need the worst case hypergraph result or?
Yes, because smooth CSPs have worst case hypergraphs. The smooth CSPs, the only smoothing is in the literal patterns, the hypergraphs are worst case. Okay, any more questions? Actually, this is a good time to stop for questions because I'm done with the results. Yes?
I guess as far as existence of certificates goes, are those existence of certificates only for weak reputation or also for strong?
Perfect. Excellent question. So the certificate I'm talking about are only for weak reputation. We actually don't know any certificate for strong reputation below the spectral threshold. Okay, very good. So, now I'm going to tell you, some actual math, tell you how these results are actually proven. And well, most of this diagram, if that is scary to you, I won't touch most of the diagram in the rest of the few minutes I have. But I'm going to explain to you what the rough plan of this argument looks like. So by this connection that Sam was making earlier at the beginning of the talk, you can actually think of, you can essentially just reduce strong refutation of smoothed K-SAT to getting strong refutation algorithms for semi-random instances of the K XOR CSP. So that's over here. So remember, semi-random means that the literal patterns are uniformly random. And K XOR CSP, if you don't know what that is, it's basically, CSP where the constraints are on K variables, and the constraints say that the XOR of them should be +1 or 0, or +1 or -1, depending on which version of bits you work with. Okay. So our life's goal then becomes, refuting semi-random K XOR instances, which, we do by breaking into two cases, even and odd. And as anybody who's worked on CSP refutation will tell you, the case of even is significantly easier than the case of odd. That's also what happens, in this result. So for evenality XOR, it turns out that you can get this strong refutation algorithm, the kind of trade-off we're after, by combining one idea from this previous work we had with the right matrix. Right matrix for CSP refutation. I'm going to explain this in more detail to you very soon. But this right matrix was invented in this very clever work of Alex Vine, Ahmed Alaoui, and Chris Moore. And this matrix is, in some sense, if I have to say one thing, if you have to remember one thing about this whole work, it's you've got to use Kikuchi matrices. Okay, this matrix that Alex, Chris, and Ahmed defined. So what we'll be able to do is take these Kikuchi matrices and actually get the result for evenality XOR by combining with this row bucketing idea. So, actually, the goal of this WAM paper was precisely to simplify the algorithms for tensor PCA and even arity random K XOR refutation. For odd, though, somehow there are difficulties. And so, they did not quite succeed. So for odd arity, we'll also introduce a variant of the Kikuchi matrix. And, we'll have to do more stuff here. We'll jump through a few more hoops, which I won't talk too much in detail, but basically there is a right Kikuchi matrix you can define even for the odd arity case and make things happen for this semi-random K XOR refutation problem. Okay. The only thing I'm going to tell you about today is, why you should love Kikuchi matrices. So I'm going to tell you why the structure of Kikuchi matrices basically solves all of your life problems. So that's all I'm going to try to convince you of the rest of the talk. Okay, perfect. So let me tell you, oh yeah, I had a fake Einstein code to go with it. Good. So I'm going to tell you how, first of all, you can use these Kikuchi matrices that WAM defined to get even arity random K XOR refutation. Okay, so all of this, none of this is our work. This is basically, older works and WAM. I hope you don't mind, Alex and Chris, if I call your paper WAM. So let's start with the case of L equals O of 1. Okay, so in this case, we are trying to get polynomial time refutation algorithms when you have n to the k over 2 constraints. Okay, and we're looking at random instances right now. So, here is how 4 XOR constraints look like. We are going to work in the +-1 world. So each constraint looks like, product of some 4 of the variables is set to +or -1. So in general, an instance of 4 XOR CSP is defined by a 4 uniform hypergraph that gives you which 4 tuples of variables appear in constraints and a collection of right-hand sides, which are simply +-1 values, B sub c's. Okay. Once you have such an instance, you can define a homogeneous degree 4 polynomial If this notation looks scary to you, it's actually much simpler than it might look. Look at this term here. For every constraint C, which is a 4 tuple, I have XC1, XC2, XC3, XC4, which is just the 4 XOR monomial corresponding to C, which I have multiplied with B sub C. So in particular, if X satisfies this particular constraint, then this term here contributes a +1. And if it doesn't, it contributes a -1. Okay. And all phi X does is average these plus or minus ones for each constraint, over all the constraints in the hypergraph. Reasonable? So, you could think of what does this phi X do actually? For any X, it computes the advantage over half of the assignment X. So in particular, if phi X is 0, it means that X satisfies exactly half constraints. If phi X is 1, it means that, X satisfies all the constraints. Reasonable? Good. So now our goal in life is to give a refutation algorithm, which means we want to give a certificate that phi X is at most epsilon for some arbitrarily tiny constant epsilon. Okay. So here's the key idea, which actually appeared in this breakthrough work a long time ago when people discovered spectral refutations in this work of Gert and Krivilovich. And the idea is very simple. We're going to write phi X as a quadratic form of a certain matrix. And once we have that, then we're going to use the eigenvalue, the spectral norm of the matrix, in order to construct a refutation. So let me tell you what that matrix is. Here's the matrix in all its glory. The matrix is indexed by pairs of variables, okay, ij and kl. And the ij kl entry is going to be b sub ij kl if ij kl is a 4 tuple that appears in your hypergraph, otherwise 0. Okay, very, very simple. Once you have such a matrix, it's actually not so hard to see that I can write down phi X as a quadratic form of this matrix. In fact, if you see, every ijkl appears 6 times here because there are 4 choose 2 ways to choose the row pair. And so that's this factor 6 here. So up to a factor 6, basically phi X really just computes the quadratic form. This vector, by the way, is simply the vector of degree 2 monomials in the assignment variable X. Any questions so far? This makes sense? So once I have, this quadratic form, I can upper bound it like we do to quadratic forms all the time. So, I can upper bound it by the L2 square norm of this X circle 2 times the spectral norm of the matrix A. Okay. So all that remains to be done. So because you can compute spectral norms, or at least arbitrarily approximate spectral norms in polynomial time, all I need to do to get a refutation is to basically prove that, this object is small when the hypergraph and the B sub C's are chosen randomly. Okay. And here, there are like basically any technique you throw at any reasonable technique you throw at the matrix actually works with fair ease. You can use Chernoff bound, you can use trace method, whatever. You can prove that this, the spectral norm is appropriately small and be done. Okay. That's great. You're done. Now let's see how to get the full trade-off. We did the case of L equals O of 1 with a very simple matrix. Now we want to do the case of L bigger than 1. Okay. So this result was first proven using a cleverly constructed symmetrized tensor product matrix. I'm not going to define this matrix for you in this work of Raghavendra Rao and Shram. Okay. Here's how we can think about it. We want to build a larger matrix that gives us like a little bit more leverage in terms of refutation. So the larger matrix that arises in their work can be seen as like writing down the matrix for a higher degree polynomial obtained by like powering up the initial polynomial you care about. Okay. So for any parameter L, you're going to get like a matrix of size n to the O of L, roughly speaking. But for our case, the analysis, in this work is fairly technical. And, it kind of crucially relies on the randomness of H. And, I don't know how to actually look at it and understand how to extend it to arbitrary clause structures or hypergraphs. Instead, and okay, a bunch of works, in fact, have tried to simplify this proof over the years. And we are going to use one of the simplifications. Okay, but the key idea, the starting point of our work is going to be the simplification that WAM did in this evenality case of random KXOR refutation. Okay. So let me tell you what this matrix is. Again, the goal is to simply write phi X as a quadratic form. But the key thing is, this time we are going to write phi X itself as a quadratic form, not a power of phi. Phi X itself would be a quadratic form of a huge matrix, like a bigger matrix. Okay. Here's the matrix. This time, it's indexed by subsets of the variables of size exactly L. Okay. you can think of the previous matrix as the case where L was 2. So now I have like blown up L. I'm looking at larger L's. The entry corresponding to S comma T equals B sub C if the symmetric difference of the sets indexing rows and column happens to be equal to a constraint C. Okay, so I'm defining this matrix A sub C for any fixed C in my hypergraph. I'm saying, I'm going to write B sub C here if symmetric difference equals C, otherwise 0. Okay. Now note that C is of size 4. S and T are of size L. L can be as large as, let's say, root n, right? So this is a sparse matrix. It has entries only when the symmetric difference is very small, like 4. But we don't mind. We're going to work with it anyway. Okay. Our final matrix is simply going to be the sum of these matrices for every C in H. Okay. Now, just like before, you can ignore the whole expression if you want to believe me. If not, you can stare at the expression and convince yourself. But basically, phi x is a quadratic form of this matrix up to some appropriate scaling, just like before. Okay. Good. So we can use the same strategy. We can upper bound using the spectral norm of this matrix A. And the key observation that works in our favor here is that A sub C's are independent random matrices. So this time A is a sum of independent random matrices, and we can apply off-the-shelf matrix concentration inequalities in order to get home. That's it. This gives you the right trade-off. Done.
Sorry, this gives it to you even for arbitrary class structure. You just need
not for arbitrary class structure, for random.
for random. Okay.
Yeah. I'll see if I can get to arbitrary class structures at the end. But for random, we are done. Okay. Any questions? Okay, good. So now I want to tell you how this particular matrix we just constructed can be used to prove Feige's conjecture. Okay. And the way I'm going to tell you is by proving this simple proposition, which of course we have several proofs for, but I'm going to prove it for, prove it with this idea that actually generalizes very easily. Okay. So I'm going to prove that if you take a 4 uniform hypergraph, random this time, and by the way, this random is simply because the analysis I just told you for the matrix A was for the case of random. Okay. But you'll see, very soon that this is a completely modular piece. So start with a random 4 uniform hypergraph with n square over L hyperedges. And I want to convince you that there is a L log n length hypergraph cycle in this hypergraph. Okay. Here's the proof idea. And it might sound absurd, but I'm going to read it out anyway. Okay. We'll prove that if there is no even cover, if there is no L log n length cycle, then if I repeat the same refutation algorithm I described on the previous slide, which by the way was for random B sub C's, but this time I'll prove to you that if there is no even cover of L log n length, then regardless of the BCs, that algorithm will succeed in refuting. That's of course absurd because I can choose B sub C's in a way that the whole instance is satisfiable. So there is no way that I can succeed in refuting for arbitrary B sub C's. Therefore, my assumption must be wrong. Therefore, there must be an L log n length even cover in the hypergraph. Okay. Now, if you go back and remember what we did in the previous 2 slides, the key step where we use randomness with the B sub C's and the hypergraph H was where we proved the spectral norm upper bound on the matrix A. Okay. So the key thing I'll prove to you now is if there are no cycles of length L log n in the hypergraph, then despite the fact that my matrix A is a fixed deterministic object, it has the same spectral norm as in the case where B sub C's were random. If this is true, then we are clearly done because that's what we plugged in to get a refutation for random case. We'll plug in the same bound, this time for a fixed matrix A, and get a refutation algorithm. But that's of course absurd. So I have a contradiction. Does this strategy at least make sense?
Wait, but at the end of the day, your goal is to get a refutation. No, I'm super confused.
That's the proposition I'm trying to prove. I'm trying to prove that every hypergraph with n square over L edges, actually only random hypergraphs, has an L log n length cycle.
And later you're going to use this proposition to get yourself a refutation algorithm that works in some parameter regime.
Not an algorithm, but the certificate.
Okay. But you will, it's just, it's going back and forth between algorithms.
Yeah, it is. But for the sake of this result, So the algorithm I want you to remember is only the thing I explained to you on the previous 2 slides, namely build the Kikuchi matrix, compute the spectral norm. Okay. Now I'm going to prove to you that that same strategy would actually go through for arbitrary B sub c's if, hypothetically speaking, there were no even covers of length L log n in the hypergraph. And that would be a contradiction because we know it can't quite go through. Okay. Yes.
Because the contradiction, because you have a signing for which you know lower bound of the spectral norm.
Yeah, I mean, I know a lower bound on the true value of the instance. I mean, simply set all B sub c's to be 1. Then all one's assignment satisfies every constraint. So I can't possibly succeed in refutation. Good. All right. So let's look at the proof of this key step. Okay. And I think I can do it in full. Okay.
That runs fast.
Okay, good.
You have 10 more minutes, including questions.
Good. I still can do it in full. All right. So long time ago, my mom told me never to do trace moment method based proof in a talk. Actually, she loves trace method, so this I'm lying. I'm going to do it anyway, okay? And you'll see it's very, very simple. Here's what trace method is if you've never seen it before. Trace method connects the spectral norm of a matrix to a trace of its high power, okay? Precisely speaking, for this matrix A that we saw before, it's true, and the upper bound is easy, but in fact, this is a reasonably tight bound, that if I take R to be about log of n choose L, n choose L, by the way, is the number of rows of the matrix. So this is simply log of the size of the matrix. If I take R to be log n choose L, which is about L log n, then trace of A to the 2R to the 1 over 2R is in fact a reasonable estimate for the spectral norm. Okay. So to analyze the spectral norm of this matrix A that I'm interested in now, I'm going to compute trace of A to the 2R to the 1 over 2R. Okay. Good. If you've ever seen this, you've seen such expressions. They look like monstrosities, but they're actually pretty tame. Okay. If I just expand trace of A to the 2R, you get a sum over choices of 2R different row and column indices, which I'm going to call S1, S2, S sub 2R. And then the product of entries of A along the path defined by this S1 through S2 2R. In fact, the walk defined by them. Okay. So in particular, this choice of S1 through S2R and the corresponding term is often called a 2R length walk on the entries of this matrix, or in the corresponding graph defined by them. Okay. Good. So that's what we want to analyze. Now, some preliminary observations. Remember how we defined the matrix A? Well, there was an entry in the matrix only if the symmetric difference of the row and column indices happen to be equal to a constraint, right? So the only way this term can actually contribute a non-zero value is if for every Si and Si plus 1, A Si sub Si plus 1 equals, Si symmetric difference Si plus 1 equals some C in the hypergraph H. Sensible? Okay. Now here is one little trick I'm going to do on you. I'm going to think of S1 and S2 as their 0, 1 indicator vectors in 0, 1 to the n. And then the fact that their symmetric difference equals C is same as saying that if I take the XOR, the bitwise XOR of the indicator vectors for S1 and S2, then I get the indicator vector for the set C. Still sensible? Okay, perfect. So each term, because my entries are like, between plus and minus 1, each term can contribute at most a plus 1. Okay. In fact, if B sub C's are all 1, then each term contributes either a plus 1 or a 0, which means that the trace is simply the number of contributing walks, meaning the number of walks for which the term is non-zero. Okay. Now, if the matrix A were random and I were to compute the expected trace of the high power, which some of you might have done in your life, then because B sub C's are random and independent, the only way a term can contribute is if the walk is returning, in the sense that every edge, every entry of the matrix is repeated an even number of times. It's because if not, then you know you're going to have a 0 because expectation of B sub C to any odd power is going to be 0. Still sensible? Which means that this trace of A to the 2R over there, the expectation of it in the random case would have been simply the sum of all walks that are even returning, meaning use each entry of the matrix an even number of times. Okay. What I'm going to prove to you is that if H has no hypergraph cycle of length L log n, in fact 2R in this calculation, then the exact same set of walks contribute to the spectral norm, even if A was fixed and deterministic. Okay. This is it. Like, this is the heart of the proof. So I'm going to pause for like 30 seconds. I'm going to prove to you that even though A is not random, A is a fixed matrix. Despite that, I'm going to prove that if you assume that there is no L log n length cycle in the hypergraph, then exact same even returning walks will be the contributing set. Which means I must come up with the same boundary spectral norm, which means that my refutation algorithm from 2 slides ago should succeed, which means I should have a contradiction. Still good? Okay, so let's see the proof of this observation.
The claim is that when you expand this giant expression, if there were no cycles, then somehow the only non-zero terms are the even, are the the ones that cover edges evenly.
Even number of times. Absolutely. That is the claim. Okay. All right, because I'll prove to you in a slide. Here's the proof. Okay, ready, Sam?
Yeah.
All right. Let's do this observation. Let's look at a contributing term S1, S2 up to S sub 2R. Okay. Let's recall, when does a term contribute? Oh, I should say this. So, a term S1 through S2R is completely described if I tell you the first set S1, and then I tell you C1 to C2R. Because, I know that S1 XOR S2 is C1. So if I give you C1, you can construct S2. If I give you C2, you can construct S3 and so on. So I can write down these equations. Okay, so far so good. Now, if I add both sides modulo 2, where I'm thinking of all these sets as actually the indicator vectors, if you will, then I must have, so notice that each set occurs in 2 equations here. So the left-hand side actually cancels out if you add modulo 2, which means that so must the right-hand side, which must mean that the sum of CIs modulo 2 must be 0. Any issues? Very simple. Okay. Good. So that's what we have. That's what we've concluded. And now it's like a one-line argument. Suppose CIs are all distinct. Suppose CIs happen to be all distinct. And you knew that sum of the CIs modulo 2 is 0. What does that mean? I claim that it must mean that the set of CIs covers every vertex an even number of times. That's the only way this can happen. But there is no 2R length even cover, we were promised. Which must mean that there is no way the CIs I choose can cancel out or add to 0 if they were all distinct. In fact, you can prove that if you take any set like this and peel off all pairs which are repeated and end up with a set which has distinct elements, then that would also have to satisfy this equality. And such a set does not exist. Which means that the only way you can have CIs like this is if each CI occurs an even number of times itself. That's the only kind of cancellation we are allowed now. But those describe even returning walks as we wanted. That's it. Perfect. Good. So, okay, you asked about the SAM, and that's the last thing I'll tell you, which is, if you want to do this for semi-random instances, so arbitrary clause structures, well, spectral norm doesn't work. In fact, it cannot. Spectral norm is actually provably too large. But you observe that the offending quadratic forms, the ones that are too large, happen to be sparse vectors. And you can actually use this in the proof using this row bucketing idea that we had in the previous paper. So it works out. For the odd case, you have to work a bit harder. You have to define the right Kikuchi matrix. And it turns out that unlike in the even case, the spectral norm of the Kikuchi matrices is large even for the case of random 3XOR. Okay, and that's my guess for why the VAM approach, kind of got stuck when trying to do this for odd. But we show that in this case, you can somehow prune away some rows. And pruning is fine because intuitively, you are again trying to bound flat quadratic forms and not arbitrary ones. Again, won't tell you much about it, But this pruning succeeds as long as a certain regularity property holds for the hypergraph. And we ensure that property by giving the new regularity lemma for hypergraph. Won't tell you about it either, but that's it. That's the main message, which is that if you randomly perturb the literals in any instance of KSAT, then it becomes as easy as random for both algorithms and certificates. The main takeaway is the Kikuchi matrices are great. If you want to prove anything about CSPs, hypergraphs, tensors, gotta use them.
Aaron, Pravesh, would you swap your laptops? And while that happens, any further questions for Pravesh? Yeah, Ryan.
I've also thought that like non-backtracking matrices can solve all your life's problems. So can you make like a non-backtracking version of this argument where just like all these even covers like just don't even exist, and so it's
perfect. It's a great question, and yeah, I can talk more offline. But basically, this is the approach I think that might succeed in removing all the polylog factors we have. So I think the use of non-backtracking matrix might actually help us tighten up this argument. On the other hand, it will also be nastier as usually this analysis goes. So yeah, together the non-backtracking walk matrix and the Kikuchi matrix solve all your life problems optimally.
And that's all, Chris. Yeah.
So I'm trying to think what happens with matrix, sure enough, in the semi-random case, if I understand the semi-random case. So an adversary chooses the clause structure, but the B sub C's are still random.
Perfect.
It's still a sum of independent matrices. What happens there?
Perfect. So yeah, Chris is like anticipating the argument for, let's say, even IDX or the kind of stuff we were doing earlier, and he's absolutely right. The clause structure is fixed, which means that the support structure of A sub C's is fixed, but still they are independent random, because the B sub C's are random. The issue, of course, is that the spectral norm is just truly too large. Because you can imagine clause structure that make some rows very heavy. If some rows are very heavy, you're going to be in trouble. But as you might imagine, this leads to only sparse vectors getting large quadratic forms. So you can imagine that some argument would allow you to bound the flat quadratic form still. Does that make sense?
I mean, one could also focus on a regular case where the no row or column is.
Then you are done.
Yeah,
absolutely. That's the so in some sense, one message of the whole thing is that if you are in the even IIT case, then the only property of the random hypergraph we happen to be using in all these fancy proofs is that no set intersects with no set S of size L intersects with like clauses in too many times. Like about as so everything is like about equally spread out in some sense. Make sense?
Okay. I think we better move on to Aaron. Aaron, thanks for being here. I think he already has. You can just leave it there. I think.